Today I am going to deliver the lecture on built up beams. In last lectures we have discussed about the design of beams with laterally supported and unsupported cases. Here we will see the built up beams how to design. First of all, why built up sections are required? As we know, when the magnitude of the load is becoming high, then the available section, available steel rolled section may not be sufficient to carry that much load. That is why we may have to go for some sort of built up section. It is not only because of that, some other reasons are there also, like if the span length is very high, length of the span is very high, then deflection will become very high, because that is some k WL cube by EI, right. So, L cube, or in case of UDL load L to the power 4. So, if this span length becomes very high, then delta is going to become very high. Delta means deflection. So, to check the deflection, but we know codal provisions that L by T25 has to be the limiting deflection. So, to check the deflection, to keep the deflection within the codal provisions, we have to make selection of beam in such a way that deflection be restricted. How do we make that? By increasing I, because WL cube by EI. E is fixed because steel section we are going to use. So, only option is I. Moment of inertia can be increased to decrease the deflection. Now, moment of inertia how to increase? We can increase only by configuration of certain section, means the beam section has to be made in such a way that the I of that section, IXX, not IYY, IXX of that section will become high. In that case, the deflection will be less. Now, see, suppose there is a say beam with a load. Now, how the moment is going to act? We know, say for simply supported, it is say moment is happening like this. Now, if we increase the load more, then what will happen? The moment is going to become more. Again, if we increase the load, then this is also increase the load. So, in the same way, the as we know that Z is m by sigma BC. That means, the section modulus, if m is going to increase, so what will happen? The section modulus, if we see, section modulus is, if it is first case, the second case it will be, this is first case, if I see the section modulus it is coming, in second case we have to go for this, and in third case maybe we have to go for this. But how long it will go? We may not have availability of that higher section. So, in that case, if still more load are there, then what will happen? Because of high magnitude of moment, we have to go with some built up section. That means, we can increase the moment of inertia and other properties by addition of some plate, additional plate. So, plate can be added, or some other built up, means other rolled section can be added, like channel can be added, or I sections can be added. In this way, we can increase the moment of inertia as a whole, or section modulus as a whole. So, in this way we can make it. However, before going to details of the built up sections, first I like to complete quickly the earlier remaining portion of the lecture. In earlier lecture, I was discussing about the design procedure of unequal beam or plate sections. These unequal flanges of beam or plate sections comes mainly when it is made built up sections. So, the design procedure which I have not discussed, I could not discuss because of shortage of time. First, let me give an overview in very shortly, then I will come to the details of the built up beams. So, in last lecture I was telling that design procedure of unequal flanges, I beams or channels. So, theory we have already told that how to find out the sigma BC, that means bending stress in compression. That how to find out, that I have discussed, and other aspects also I have discussed, that how trial and error method we have to find out, what are the parameters, what are the expressions to find out FCB, elastic critical stress. Then for finding out FCB, what is the different parameter like x, y, which can be find out from expression or from the table which is given in 6.345. in different table different values are given, coefficients are given. So, from that we can make. So, now we will just have a look the what are the procedure we used to follow for design of such sections. So, first is that from steps 1 to 4 in design of laterally unsupported beams with unequal flanges will be same as in the case of laterally supported beams with equal flanges. So, steps 1 to 4 whatever we have discussed in case of laterally unsupported equal flanges will be followed for the case of laterally unsupported unequal flanges. That means, step 1 to 4 will be provided for laterally unsupported unequal flanges also. Now, step 5 will be differ from the laterally unsupported equal flanges with this. What is step 5? In step 5, we will find out the elastic critical stresses using this formula, that is FCB is equal to K1 into X plus K2 into Y into C2 by C1. Right. Now, the coefficient of K1, K2, X, Y all either can be found from the tabular form given in code in IS 800/1984 in table 6.345. Otherwise, we can find out from the expressions which was shown earlier lecture and also given in the code at corresponding clauses. So, from there also directly we can find out. As I was telling, if we go for development of a software program to design such beams, we need to calculate the values by the use of expression, not by the use of table, because in table certain values are given from these equations. Now, if we put directly these equations, we can find out the exact value for a particular case, which we do not need to extract from the table. So, if we can develop a software properly, we can utilize our time, we can save lot of our time for designing such beams. When in a design office, a design engineer is going to design such type of things, they can use such software to save the time, and by using such software they can make the design economize, means they can find out a very suitable section which will be economic from cost point of view. So, in that way they can do. Because of manual calculation which is very much tedious, generally design engineer is reluctant not to do the iteration, that means again and again they are not calculating. But if he has the software, then the computer itself will through search, through iterative, they will find out the appropriate section which will be most economic, right. So, I will suggest the students, those who are learning this course, to develop their own software, so that it will be useful for their own purpose as well as for others. In step 6, what we will do? The value of permissible bending stress in compression is calculated for the calculated value of elastic critical yield stress and selected value of yield stress. This may also be found directly from table 6.2. So, from table 6.2, with those also we can find directly the elastic critical stress and sigma BC, that is also possible. Now, in step 7, the moment of resistance of the section is calculated using the same formula used in design of laterally unsupported beams with equal flanges. So, similarly, we can find out the moment of resistance, that means Z into sigma BC, right. And step 8 will be as usual checking for shear, whether the developed shear stress is exceeding the allowable shear stress or not. If it is exceeding, then we have to redesign, otherwise it is okay. And then finally, check for deflection, the deflection of the beam, whether it is coming within the limit of the coral provision or not, that we have to check. So, in this way we can design an unequal flanges of beam and plates which are unsupported laterally, right. So, this was the things which I could not finish in last lecture, we have discussed here. Now, you can start with some sort of problem, some example for this kind of problem you can do at your own, and it is very simple, because in table 6.2 you will get the data, and table 6.3, 4, 5 you will get all other necessary data to find out, and the procedure will be exactly same as we have done in case of equal flanges unsupported beam. So, procedure will be exactly same, only the value of sigma BC will be changes, other things will remaining same. So, I am not going to solve another example for this, rather I will start some other things. So, what I was discussing in the beginning for today's lecture, that is the built up section. So, the gist of the requirement of the built up sections can be told in this way, that the available rolled steel sections are insufficient to carry the high magnitude of the load. If load is becoming very high, then the available sections may not be sufficient to carry. So, in that case we have to use some built up section, where the additional plate or other members will be used. Sometimes the depth of beam is restricted. Yeah, suppose we cannot go beyond certain depth. So, if we use a higher section of say I section or some other section, that may exceed the limiting depth of the beam due to certain architectural or other purpose restrictions. So, in that case the built up section means with lesser depth with some additional plate we may have to go, right. Another is, if the span is too long, but the load is light. So, in that case also we may have to go for built up section, because unnecessarily we cannot provide heavier section, because that will be uneconomic. So, to make economic we can provide two section with a proper configuration, so that the section means the modulus the moment of inertia of the compound section become very high, right. So, built up sections are basically of three types. One is generally what we used to do, that I section or any section with some cover plates. So, cover plated beam section, I sections it may be, some channel section it may be. So, like this we can make. Another is compound beam, that means I section with channel section, so maybe like this, right, or channel section with another channel section. Okay. So, such type of things may come into picture. Another is combination of the last two, that means combination of these two, that means maybe this I section along with plate section and channel section, right. So, different type of built up sections can be made. Some of the built up section let me draw here. One is generally, which is the most common, is that I section we used to make with some additional plate, and this may be riveted or welded, this can be done, right. Another section we use is, I am just showing here those which are commonly used in practice, say I section with some channel section at the top, right. Other is say maybe two channel sections with some plate, maybe at the top, maybe at the top and bottom, whatever it is. Another is say two channel section along with another two channel section, right. Okay. Another is say I section, two I sections we are providing, then we are providing plate. Okay. So, all these things depends on how the load is coming, what are the magnitude of load is coming, in what way it is coming. So, according to that we have to find out the configuration of the built up section. This is another section, say only we are providing at the top, right. Another section is say two I sections are provided in this way just to increase the depth, right. So, you see, so two small I sections can be placed, one in top, another in bottom, so that the moment of inertia of the section becomes high, and this is basically to tackle care this case 3, that if span is too long, but the load is light. So, for this case generally such type of sections will be suitable. Now, we will see how to design a cover plate. Means as we are seeing that built up section means the some rolled section along with some other additional section. So, suppose if we use a cover plate, how we will calculate the properties, let us see. Say one I section is given, so this is a I section, and this is a cover plate, right. Now, the thickness of the plate, say let us have Tp, thickness of the plate, and width of the plate let us make B, and say center to center distance of the plate is say small d, and as we know this is capital D, the depth of the section, rolled section. Okay. So, if we rename the parameters of this configuration in this way, that d, small d is distance between the center of the flange plates, and Tp is the thickness of the flange plate, and d is the depth of the available section, depth of the available section, that means this one d, right. If it is so, then how do we find out the cover plate dimensions? Now, AP can be written the area of each flange plate, which will become B into Tp, because B is the width of the plate and Tp is the thickness of the plate. So, B into Tp. Now, I we are assuming as moment of inertia of the available section, that means moment of inertia of this I section, moment of inertia of this I section, right. So, with this parametric symbol we can write that I is equal to I plus 2 AP into d by 2 whole square. This is, we are assuming that symmetrical built up section, that means the plate of this and plate of this, top plate and bottom plate are same, area is same, thickness is same, everything is same. Okay. So, with these assumptions we can write I will become II plus 2 AP, because if this is I, so when we are making means moment of inertia of the whole section, so this is I section, right. Now, when we are going to make some plate here, this is I section, right. So, I will become II means I have this plus 2 AP, 2 into area of plate into d by 2 whole square, because if this is d, then from neutral axis to here it will be d by 2. So, d by 2 whole square. So, we can rewrite this as II plus 2 AP into d by 2 means that capital D by 2 plus TP by 2. This is total D. So, this will become d by 2 and this will become TP by 2. So, and this total is basically d by 2. So, d by 2 is nothing but d plus p by TP by 2, d by 2 plus TP by 2. So, AR square means 2 AP into this square. Now, Z will become I by Y max, right. So, I means this one which we have found here I. So, I by Y max is this one, right, d by 2 plus TP by 2, because d plus TP is the total, right. If I draw here, it will be clear. Say I is this one and this is plate, right. Now, here will be the maximum stress. So, I can find out this distance will be d by 2 plus TP by 2 at this, right, and we are making, actually it should be d by 2 plus TP, right, but for dividing these two we are approximately making like this. Since you see TP is usually unknown, an approximate expression for Z may be written by assuming TP to be small compared to D. So, we are taking some approximation to get the value of Z appropriately. So, what we are doing? So, Z we are going to get in this way, and if we make I by this at Zi plus AP into D, right. If we derive this equation, we will find out finally as Z will be approximately Zi plus AP into D by neglecting the TP in some places, because D is much greater than TP, otherwise we have to calculate as a whole. So, now if Z is required section of the plate beam, then area of the flange plate required will be this, because Z minus Zi by D. From this equation I can find out AP is equal to Z minus Zi by D, right. So, the above expression is based on the assumptions that there is no hole in the tension flange. First of all, so area of plate we are going to get approximately, it is not exactly, Z minus Zi by D, where Z is the total section modulus and Zi is the section modulus of the roll section, means available section, and D is the overall depth of the section. So, from this we can find out AP. Now, again we are assuming that there is no hole, and in this basis we are making, but we know when we are going to make an built up section, either we have to connect through rivet or weld joint. So, in case of rivet joint we have to make some hole. So, the net area will be going to reduce, net area of the plate is going to reduce. So, the required area of plate AP needs to increase up to certain percentage, so that after deduction of hole this AP will become sufficient to carry that much load. So, for designing purpose we will increase some percentage of AP to find out the proper dimension of the plate. So, gross sectional area of the flange plate is generally taken 10 to 20% more than the net cross sectional area given in the equation above, to allow for rebates and approximate calculation. First of all, we have made approximate by neglecting some places the TP compared to D. Okay. Another thing is because of the hole, because of providing hole due to rebate, we have to find out the net area which is less than the gross area. So, we need to increase the percentage of some percentage for the gross area, so that the net area become equal to more or less that AP, so that it can withstand that much load. Okay. So, as you know, AP is equal to B into TP. So, that say 1.2 into AP we will find out finally, right. Now, the moment we are going to get AP, area of the plate, now we have to decide what will be the thickness of the plate and what will be the width of the plate. Some guidelines has been given by the code IS 800/1984. In clause 3.5, the plate thickness has been described. Plate thickness of the section means the additional plate, whatever it is, that has been told there. It is told that the outstand of cover plates, flanges, waves, angle legs should be within the limits to avoid local buckling, because plate cannot be made abruptly, because local buckling may happen. So, outstanding cover plates, flanges, waves, angles, etc. has to be within limits, and that limits has been specified by the code. Now, code has given some provisions which I am going to write here, so that we should have some idea before going to design a built up section, right. So, in code, in clause 3.5, it is been told that it depends on the type of plate, and then accordingly the maximum width. For different type of plates, maximum width has been decided. Say like if the flanges and plates in compression unstiffened, then the maximum width will be 256 T by root over Fy, and that is subjected to maximum of 16 T, where T is equal to thickness of single plate or the total thickness of the all plates, right. So, this is one case may happen. Second case is flanges and plates in compression but stiffened. So, in this case this will be 20 T. So, flanges and plates in compression with unstiffened, this will be maximum 16 T, and flanges and plates in compression with stiffened plate, it will be 20 T, and flanges and plates in tension, this will be the maximum width will be 20 T, right, where T is the thickness of a single plate or the total thickness of two or more plates effectively stacked together. So, this is the T. T is the thickness of a single plate or the total thickness of two or more plates effectively stacked together. So, this is the T. Now, for built up members, say for built up members, let us see how the thickness and maximum width are defined by the code. Say type and say maximum width. Say case 4 now, say compression member, this is for built up member, right. Compression members, plates like waves, flanges, cover plates in uniform compression, right. For this, the maximum width will be 1440 T by root over Fy, subject to maximum of 90 T. However, when the width exceeds 560 T by root over Fy, subject to a maximum of 35 T for weld plates, which are not stressed relieved or 800 T by root over Fy this place is type and this is maximum width. So, it was writing that 800 T by root over Fy subject to a maximum of 50 T for other plates, right. And number 5, which is last one, for plates in uniform tension. For this case, this will be 100 T, right. So, plate thickness and outstand are depending on the type of plate. and for plates in uniform tension the maximum width can be taken as 100 T. So, in this basis means with these codal provisions we have to decide the thickness and width of the plate, because already we can decide the area of plate. Now, the moment we decided area of plate, we have to find out what should be the thickness and what should be the width, so that area of plate become that much, means that constant. Okay. That means AP will be equal to TP into B. So, how it will be distributed, it depends on the codal provisions. As per the codal provisions, we have to adjust, we have to suitably decide what should be the width and then what should be the thickness. Now, we will discuss about the bending stress in built-up members, how the stresses are going to develop in case of built-up members. As you know, the built-up members means either the connections will be riveted or welded. In case of welded connection, the calculated bending stress are not affected. So, calculated bending stress are not affected, but for riveted connection the stress in the tension flange is more due to reduction of area by the rivet holes. So, stress will be more. Therefore, net and cross sectional areas are calculated and bending stress in tension is calculated as follows. So, bending stress in tension will be calculated like this: sigma BT calculated is equal to sigma BC calculated into gross area of tension flange by net area of tension flange. That means, we know what is the gross area of tension flange, and we know because of the number of holes due to the rivet what is the net area of the tension flange. So, we have to multiply that ratio with the sigma BC cal, so that we can find out the sigma BT. Now, we will go through one example through which we will be getting some idea about how to handle the built-up sections. In fact, first example whatever I am going to show here is a part of that, means it is not the end of the built-up sections, because other aspects like curtailment, like how to design the connections from shear point of view, etc., those things I will come later. But before that, whatever we have discussed here, on that basis let us try to work out one example. A simply supported beam is built up with a channel ISMC 200 at 22.1 kg force per meter attached to the top flange of ISMB 400 at 61.6 kg force per meter. Calculate the maximum central load that the beam can carry over a span of 10 meter when the bending stress is limited to 165 MPa. Right? Neglect the self weight of the beam and assume that the beam is laterally supported. So, we are going to neglect the self weight of the beam, that means as it is less. So, let us neglect, then with neglecting the self weight of the beam, we will try to find out what will be the load carrying capacity of that beam, means what will be the maximum load centrally placed for this particular beam. So, what are the things are given, that this is a first of all simply supported beam and carrying a central load say W, and the length is given, that is 10 meter, right. And if we see the section, so section will be looking like this. Okay. So, this is ISMB 400 and this is ISMB MC 200, right. So, sections are placed like this and loading conditions are like this and end conditions are like this. So, from this we have to find out what will be the maximum central load that beam can carry. Okay. So, what we will do? So, we have to find out the relevant properties from handbook, that SP6. From SP6 we can find out the relevant properties of IS MC 200 and IS MB 400. Say for IS MC 200, what are the things required is the area, cross sectional area is given as 28.21 centimeter square, right. Similarly, CY means from this, if we see, this will be the CYY, that is 2.17 centimeter, and IY is 140.4 centimeter to 4. IY means if we see the channel section like this, this will be IY, because here IYY will be this one and IY will be required for us. Similarly, for ISMB 400 we need area is given 78.46 centimeter square and IX is given as 20458.4 centimeter to the power 4. The moment of inertia is given. So, with this value what we can do? We can take the moment of inertia about the fiber to locate the neutral axis of the section. About which one? The top fiber. So, if we take moment of inertia about this to locate the neutral axis, we can say that total area into y bar, total area is this 78.46 plus 28.21. So, total area into y bar means say if neutral axis is acting here. So, this is y bar, distance between extreme fiber at the top to the center to the neutral axis, right. So, this is equal to 78.46, this is the area of the I section. So, 78.46 into area distance will be its individual neutral axis is here. So, from here to this will be 200, because this is ISMB 400. So, this will be 200 plus the thickness, this thickness was given. So, 200 means 20 centimeter and thickness was given 6.1 millimeter. So, that is TW, thickness of the wave of the channel section. So, 20 plus 0.61, and similarly area of the channel section, that is 28.21 and then 2.17, right. CY is 2.17. So, in this way we can find out, right. So, y bar is becoming 15.73 centimeter, right. So, neutral axis depth from top fiber we can find out. Now, we have to find out the IX, means moment of inertia of the built up section about this, right. So, IX will become IX of the individual section of the I section plus AR square, because of shifting. AR square means this distance we know, because 200 minus this y bar, okay, 200 minus y bar, or we can simply find out what is the distance, then we can provide, you see, this plus 0.6 minus y bar. So, we can find out the shifting, means moment of inertia due to shifting of the neutral axis, then neutral axis of the channel section. So, finally, we will get 27457.34 centimeter to the 4. The viewers can calculate the moment of inertia about x axis at their own, because in other way also you can find out whichever you feel easy, you can calculate in that way. Finally, the results has to come same. Next, what we will do? Next, we will find out ZX, section modulus, from compression side. From compression side, we can find out this is y bar, this is I. So, Ixx by y bar. So, we are getting Zx is like this, and Zx from tension side we are getting, this is total depth minus y bar, that means from bottom side. So, this we are getting like this 1103.6, right. So, in this case, as it is told that sigma Bt is equal to sigma Bc, means because of laterally restraint, means at the question itself it is told that the sigma Bc and sigma Bt can be found, means can be assumed as 165. So, moment of resistance will become M is equal to sigma Bt into Zx, because this is less, this is more. Okay. So, failure will be at the bottom first due to tension, right. So, M will become this, after multiplying this we will get like this, right, 18209.4 kilonewton centimeter or 182.094 kilonewton meter. Okay. Now, if the W is the central load on the beam, then maximum bending moment we can find out WL by 4, because for a simply supported beam maximum bending moment will develop like this, that is WL by 4, if this is W and this is L. So, WL by 4, that means L is 1000, sorry 10 meter it was, so 1000 centimeter, so WL by 4 is coming this. So, now if we make equal means the moment developed due to load and the moment resistance capacity. So, from these two we can find out the load carrying capacity as 72.83 kilonewton. So, W we are getting the load carrying capacity, central concentrated load for this particular beam is 72.83 kilonewton. So, this is how for a compound section, for a built up section we can find out the load carrying capacity of the beam, right. Here you can observe that we have not given, means we have not gone to details of the couplement, connection, riveting or welding, other things we have not gone, which we will go step by step in details, right. Just to freshen up our study, means whatever up to whatever we have done, on that basis we just solve this problem. Next we will discuss about the design of connections, right. Now, as we know, connections means connection between the plate and the main section. That means, if we have a I section along with additional plate, then the flange of I section and the plate has to be connected properly, so that it acts monolithically, and the connections may be done through riveting or welding. Okay. In rivet connections, generally rivets are staggered to obtain more net area. So, when we are going to connect, say if I see from top, if this is the plate which is connected with the, say this is the flange, from top if I see, so it should be some sort of staggered, not in same line, so that the net area can be obtained more. So, in this case failure will be either here or here or here, means one hole only we are getting. So, net area will be more, otherwise the failure may happen like this, like this, like this, where also the net effective area will be more, means in place of 2 in same line it will be very less, right. Now, the nominal diameter of the rivet is assumed and then the pitch of the rivets can be computed. So, while designing for connections, what we can do? We can find out some nominal diameter. Finding out means we can assume some nominal diameter, then as per the codal provision we can find out some minimum pitch. Okay. So, pitch also we can find out. Now, to find out the shear stress, let us denote this tau as shear stress at the section, and let us assume V as the shear force at that section and I is the moment of inertia of the whole section, right. Tau is the shear stress at the section, V is the shear force at the section and I is the moment of inertia, right. And other things like B is the width of flange plate at the section, width of flange plate at the section, and A y bar is the moment of area about the neutral axis above the section considered. That means Q, VQ by IB we used to provide for getting the value of tau, VQ by IB. This Q is nothing but A into y bar, right. And let us assume that tau 1 is the shear force per unit length and S is the pitch of rivets. Okay. So, with this parameter we can write the shear force at the section, means shear stress at the section tau is equal to VQ by IB, okay, where B is the width of the flange of the plate and V is the shear force at that particular section, I is the moment of inertia of the whole section and Q is nothing but AY, that is moment of area about the neutral axis above the section considered, where we are going to consider that one. So, shear force per unit length we can find out, that is will become tau 1 is tau into B, right, where B is the width of the section. So, tau 1 can be find out as like this, because tau was V A y bar by I B, right, and into B. So, this will cancel. So, we can write tau 1 as V A y bar by I. Thus, the horizontal shear force per pitch can be calculated. Now, shear stress per unit length is this, means shear force per unit length. Now, so shear force per pitch length can be find out if we multiply with the pitch, where S is the pitch, right. So, this is the horizontal shear force per pitch length V A y bar by I into S. Now, how many rivets are there per pitch? Okay. We can assume that if the rivets are provided in n rows, means how many rows are there. So, let us assume the rivets are provided in n rows, then the horizontal shear force is shared by equally n rows of rivets, and the rivets in each row are subjected to a horizontal shear force per pitch length. That means F will become total by n, because n rows of rivets are there. So, shear force is going to distribute to that n number of rows. So, finally, F is going to become V A y bar S by n into I. So, per pitch means per rivet, sorry, in every rivet this much force, shear force is developing, this much shear force is developing in every rivet, and the rivet has to carry this much force. So, we can say this has to be becoming as rivet value. That means the rivet value per pitch length can be written as RV is equal to this one, right, V A y bar S by N I. Now, if number of row is 2, we can write RV is equal to V A y bar S by 2I. If number is 1, then simple I. So, depends on that. Okay. For n is equal to 2, RV can be written like this. So, in this way the rivet value per pitch length can be find out. Now, we know for a particular diameter of rivet what is the rivet value, and the value whatever it is coming here we know. So, from that we can find out that whether the rivet whatever we have provided with a particular pitch and with a particular number is safe or not. Now, the code has given some provision for providing pitch, that the pitch should be checked for the following, because we cannot provide arbitrarily the pitch, we have to maintain some codal provisions, right. So, what are the things? Let us see. First is the minimum pitch should not be less than 2.5 times the nominal diameter of the rivet. Minimum pitch should not be less than 2.5 times the nominal diameter of the rivet. This is one. Second is the distance between two adjacent rivets parallel to direction of stress should not exceed 16 T or 200 mm, whichever is less on the tension side, or 12 T or 200 mm, whichever is less on the compression side. So, while providing the pitch distance, we must take care of all these codal provisions. What are the other codal provisions? Other is like the distance between two adjacent rivets should not exceed 32 T or 300 millimeter, whichever is less. The distance between two adjacent rivets should not exceed 32 T or 300 mm, whichever is less. Another is for staggered rivet joints, if the gauge distance does not exceed 75 millimeter, the distance specified in 2 can be increased by 50%. Specified in 2 means this one. Here we specified the distance, so that can be increased by 50%. That is, for staggered rivet joints, if the gauge distance does not exceed 75 mm, the distance specified in 2 can be increased by 50%, right. Then another option is that for welded connections, intermittent fillet welds are provided. For welded connections, intermittent fillet welds are provided. So, these are the provisions which has been defined in code. We have to remember before deciding the pitch distance for connecting plate with the flanges, right. Other things are curtailment, that sometimes we have to see that the plate whatever we are using, additional plate may not be required throughout the length of the span. Unnecessary we do not need, because moment is going to reduce as per the end condition and loading condition. So, where the moment is less, we can provide less section, that means we can reduce, we can omit the additional plate, and where the bending moment is more, we can introduce some additional plates with length. So, that also has to be taken care properly. How it will be, we will see in next class. So, today with this I like to conclude, and tomorrow we will start the remaining part. Thank you very much.